Okay, here's the title, Linear Functions. We've been talking about lines for a while now. What about that word functions? What does that mean? Let's spend a little time talking about it. A very important word in mathematics. Okay? I'll do it over here. I think of a function as being a machine. Okay, it's a machine where you put something in, put some numbers in, and the machine does something to it and spits something out. Okay, since function, the word begins with F, we usually use F as one of our symbols for a function. And f of x basically says, here's what this function does with any x that you stick in. I've got a function in mind. See if you can guess what it is. If you put in a 0, the function whirls around and spits out a 1. If you put in a 1, it does something to it and spits out a 2. Okay? Do you know what function I'm talking about? If you put in a 2, it whirls around and spits out a 5. Catch you by surprise? Stick in a 3 and a bunch of noise and such, and it spits out a 10. Okay? Do you know what's going on here? If you put in a negative 3, it also spits out a 10. Can you see what's happening? Let me do one more. You put in a 4, what comes out? Did you guess 17? Here's the function I have in mind. Whatever number you put in, this function squares it and then adds 1 to it. Okay, that's what it does. Given any function, all the numbers that you can put into the function, these are just a few of them. You can put in not only nice numbers like this, but you can put in all the numbers along the real line. Pi and e and 2.137696. All those numbers you can put in is called the domain of the function. And all the numbers that come out is called the range or the image. Okay? So that's kind of the guts of what a function is. And whenever you have a function, it's typically because you're interested in how it behaves. And when you're interested in the behavior, you're interested sometimes in when is it decreasing, when is it increasing, how low will it go? Maybe it has a minimum value, maybe it has a maximum value, all sorts of things like that. You kind of want to know about it. And so you've heard the phrase, a picture is worth 1,000 words. If you can draw a picture of a function, you can usually answer most of those questions at a glance. And so the way you draw a picture of it is just by making a table like this again and letting the x value be the point in the domain that you stick in, and then letting the y value, since you're going to graph this on the xy axis, letting the y value be the value that comes out of the function. So each one of these things forms an ordered pair then. We have the ordered pair 0, 1, 1, 2, 2, 5, 3, 10, and so on. So those are all going to be points on our graph. And if you graph all those points, here's 0, 1. I'm not going to take time to do it, but it ends up looking something like that. Here's the point 1, 2, 2, 5 right there, 3, 10 right there. Here's 3, negative 10 is right there, or negative 3, 10. So there's what the graph looks like. And once you have the graph, then as I say, you can determine where is the function decreasing, where is it increasing, what's the smallest value that it takes. In this case, it looks like the smallest value is 1. The largest value, there isn't any, right? It just keeps going up, 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 up. And so that's what functions are. We're going to return to these particular functions in the next chapter. But for now, I kind of like that as an example just to show you what a function is. Okay, so we're going to look at linear functions. And as you might guess, a linear function is just something of the form ax plus b, where if you graph it, if you let y be the value of the function that comes out, then what you're going to be graphing is going to be some sort of a line. So this chapter is very much like, or this section is very much like previous sections, instead of putting y equals ax plus b here, we're going to write f of x, where f of x means something. It could mean population or temperature or something like that, but it stands for something. But then when we graph it, as soon as we graph it, we let this value be the value of the y value of the coordinate, and so it ends up being a line. So anyway, the author has several examples of where the natural world comes up with linear functions. I'm going to give you a couple from my own experience. I had a dog who died a couple years ago, but he lived with me for 12 years. His name was Elvis. He was a Welsh Corgi. If you know what a Welsh Corgi looks like. Okay. Hold on just a second. Okay, look at here. Here are some things, pictures of Elvis and me. This was in the Holland Sentinel. This is when he first became famous. See that? My dad showed that proudly to a friend of his, and his friend said, "Yes, I saw the picture. What an intelligent looking dog." I was teaching at Hope College at the time. Here is a picture of Elvis there. Isn't that handsome? Dogged researcher. This was a couple years later when we headed off across country on some sort of event. Here's a picture of Elvis on the front of a math journal. The ball in his mouth. This was the original journal right here, where he's at the beach with, I don't know if you can see everything, the ball and tape measure and Phillips screwdriver there, everything else. Okay, so let me tell you the Elvis story. I went to the beach with Elvis, and I would stand along the beach right here. This is the water and the beach, and Elvis was right with me, and I would toss the ball there into the water. And instead of swimming all the way to the ball, which would have been the shortest distance, Elvis instinctively knew that he'd get there faster by running along the shore a ways, since he runs faster than he swims, and then he swam the shorter distance. Okay? So I did the calculus to find out what would have been the optimal point for him to have jumped in order to get there the quickest. And so what I did was I practiced throwing the ball so that the ball, I taped a tape measure to the beach right here, and I threw the ball so that the ball would lie somewhere along this line, and then I threw it, and Elvis went jumping after it, and I went racing after Elvis with this big Phillips screwdriver in my hand. And at the point where he jumped into the water, I plunged the Phillips screwdriver down into the sand. I had people at the beach saying, "Why are you chasing your dog with this Phillips screwdriver?" I had to explain I'm doing a science experiment. So anyway, he's racing towards the ball now. I quick run out. I grab the free end of the tape measure, and I run out, and I get to the ball before he does. He's not that fast of a swimmer. I give him the ball. He brings the ball back. Then I took this distance there. That was X. And then I also measured back to where the Phillips screwdriver was. That was Y. And so I then came back to my office, and I plotted all these points, X comma Y, where X was the distance of the ball into the water and Y was Elvis's choice. And there were about 35 of them. And when I plotted them all, they were, kind of all over the place like this. And it turns out that when I did the mathematics to determine what would have been the best choice for Elvis to jump in, here's the X coordinate, there's the Y-axis. It turns out that this red line right there was his best choice. So that red line gives the optimal choice, and notice that all of his choices were pretty close to it. He was typically within about a foot or so, maybe a foot and a half of the optimal choice. So very cool. So there's an example of using lines to kind of model what's going on in the real world. Here's another one I did, okay? That's one of my, that one I'm well famous for, okay? If you go and put in Elvis and Welsh Corgi and put in calculus, just Google those, you'll find all sorts of stories about Elvis and me with that thing. We've probably given 300 talks all around the country in the time that he lived. He died now about 5 years ago. He lived a good long life, but he was world famous. Okay, so Queen of England knew about him, everything else. So did I tell you? Ellen DeGeneres wanted him on the show. So here's another experiment that I did once. I was about to play racquetball with a friend at the gym, and I happened to pass the women's volleyball coach on the way to the racquetball court, and she knew I was a mathematician, and she asked me this question. She said, "Can you help me instruct the gals on the team as to how they should serve the ball so that the ball obviously goes over the net, but then comes down close to the net, within 5 feet of the net, as quickly as possible." Okay, she didn't want one that went way high and came down real slowly. That would be easy to return. She also didn't want one that went way out here, because that's easy to bump and return as well. This was the optimal. And it turned out that the person I was playing racquetball with that day was a retired physicist from NASA, worked at NASA. And so we ended up kind of trying to think about it as we were playing racquetball, and I ended up giving it to a couple of research students, undergraduate research students over the summer. And we did all the calculations to figure out what the optimal path was. And if you think about it, gravity, of course, is a very important factor, and the air resistance is an important factor. But the other thing, what's the third thing that's important? The spin of the ball. If you ever watch I play table tennis a lot. If you play table tennis or soccer or tennis or volleyball, the spin of the ball really affects it being able to come down faster like that. And so what we needed was some way to determine what is the force due to the spin on the ball. And here's what we came up with. I think it was kind of ingenious. We had on campus, we had a balcony which was about 30 feet up. Okay, so here's this balcony, here's the floor. And so here's what we did. We got a volleyball, and we put two little cups on both sides of it where we put holes, and we had little dowel rods that stuck out of those cups so that we could hang on to the dowel rods and spin the ball. Then we put a blue line and a red line on this ball so that we could watch it spin when we had a video of it. I'll make it green and red. So there they are. So they're on this ball. Then this took 3 or 4 people. Then we wrapped a string around it, and we zing, got the ball spinning really fast. As soon as it was spinning fast, then we took a video of the ball to see how fast it was spinning. And then the fella who had the ball with these 2 dowel rods, he just dropped it off the balcony, dropped it from right here, and it went down. Now, if there was no spin on the ball, it just fell straight. But with that spin on the ball, it was amazing to see what would happen. It went vroom. It actually really, especially as the speed increased, it really deviated. And so each time it fell, we put a little sticker right there, and we indicated that that was trial number 13. And then we went back and we saw what the speed was at 13. And then here's what we did. We made ourselves a graph, and this was the spin of the ball. This is how fast it was spinning, and this was how much it deviated. Deviated distance. And it was amazing to see the relationship between those two things. It was almost perfectly a straight line. Very, very cool. And so the slope of that straight line gave us basically the force due to the effect of spinning. Okay, so another neat example of using lines, and where lines just kind of come in naturally. Okay, so anyway, those are just a couple I wanted to tell you about. Here's one from the book, and I'm going to take it right out of the book because I think the author provided us a very nice problem. Okay, let's just look at it. He says you and a bunch of friends have a garage band, and you've made a DVD of your garage band performance. Okay, and you're making the DVDs, so the cost is, first of all, it took you $100 to advertise, and each of the DVDs that you make costs $20. Okay? And then your revenue, the amount of money that you bring in, is you sell them for $24 per DVD. Okay? So you want basically some sort of a graph that expresses the relationships of these two things and gives you a sense of how many you need to sell in order to make money and things like that. So let's graph both of them. Let's let X, remember that word let again? Let. Let X be the number of DVDs that you've sold. Okay? It's the number of DVDs you've sold. And so, well, just say, yeah, well, number of DVDs. Yeah, I guess so. That's good. And let's assume that you can make them. You make them for $20 as they're asked for. So you don't have to make them in advance. As people ask for them, you can make them. Okay. So those are the ones that are both made and sold. Okay, both made and sold. Sold and made. Let me put that on there. Okay. So anyway, what's the cost going to be? What's the cost as a function of X? You're going to spend $100 whether you make any DVDs or not. Agreed? So that's going to be $100. And then for every DVD, it's going to be another $20. So that's going to be the cost. And so if you want to graph that, it's going to graph something like Y here. And so this is always going to be your value of Y, is the value of the function. So it's going to be 100 plus 20x. And I'm not going to worry about whether it's 20 units high. That would be awfully high. I'm going to just make it look like this. Okay? So there's your C right there. Now, what's the revenue? Let's use R for revenue. The revenue is just going to be $24 times the number that you make and sell, right? 24x. What kind of a line is that going to be? That's a line going through the origin. It's going to have a steeper slope than this one, though. It's going to look something like that. So there's your revenue. And here's your cost. 100 plus 20x. Can you see that? There you go. Okay? So we want to know kind of what's the break-even point. Where are those two things going to be the same? And we can easily do it. We can say, okay, where will the revenue be equal to the cost? And so we just set them equal to each other. 24x is equal to 20x plus 100. Subtract 20x from both sides, and you get 4x is equal to 100. X is equal to 25. How easy was that? So at 25 discs, that's where you break even. If you sell less than that, you're going to be hurting. Well, yeah, you're going to be hurting because you still spent this money for advertising, and if you sell more than that, you're going to be going up there. That's going to be good. So that's kind of cool. Another way to do this problem, this is the way the author did it. Another way to do it is to say, hey, let's let the profit be equal to the revenue minus the cost. Do you agree? The profit is the revenue minus the cost. So in that case, the profit, let's go ahead and do it over here. P of x is equal to R of x minus C of x. And so if you take this and subtract this, you're going to get 24 minus 20 is going to be 4x minus 100. See that? 4x minus 100. If you take the revenue minus the cost, you're going to get 24x minus 20x is 4x, and then 0 minus 100 is negative 100. So now if you were to graph that, that gives you really everything in one scale, in one graph. So now you have a graph which has a y-intercept of negative 100 and a slope of 4. So again, this is the number that you make and sell, and then this is your profit now. So this is your profit. Okay? So now, basically, I think it makes it a little bit easier. See this? You can first ask, where will the profit be equal to 0? That'll be where 4x is equal to 100, which is when x is going to be 25. So there's your break-even point. That's where you have a 0 profit. If you sell more than that, then you're going to have a positive profit. If you sell less than that, then of course you're going to be losing money. So that's another way to do it, is to actually subtract the one from the other. So anyway, nice problems. Quite often, by the way, just as an aside, quite often in business, you do end up with a graph that looks like this. Those of you who are in business, this is kind of important to realize. This is your cost. This is the cost function. Okay? And why does it look like that? It's because you have a fixed cost, which is your advertising or the price of the machinery or the price that you're paying just to open the doors of the building. Quite often there's a huge fixed cost to a manufacturing plant especially. If you're just doing something simple on your own computer, then there's not much fixed cost. But if you're investing money into it, whatever that investment is, that's your cost before you ever get anything. Then you have the cost of production. And the cost of production is basically how much does it cost to make one more unit. So if you just make one more unit, this moves over 1, what's the added cost? And so those are two important things. So for example, if you're selling things, out in public, you want to set your price. You want to set your price so that pretty quickly you will end up hitting this break-even point, right? You're never going to ask that first person to pay all your fixed costs for you. They're just paying. If it's DVDs, they're paying $4 per DVD. So it's 24 for one DVD and it's 48 for 2 of them. It's just going to be a straight line like this. So they don't make up that whole thing. But you need to set your price so that eventually, hopefully as quickly as possible, you'll catch up and you'll be in the positive territory there. On the other hand, if you had a good friend or your mother or someone like that came and said, hey, can I have one of your things that you make? Well, then maybe you'll just want to sell it to them for what you make it for. So then this is called the marginal cost. This is just how much it costs to make one of them. You're not really concerned with the fixed cost then. You just say, hey, you want one because you're my mother, I'll make you one, and here's the cost. This is what it costs just to make this particular one. Forget about all the fixed costs involved. So that's called your marginal cost. Okay? So, very good. All very important stuff for anyone in business to understand. Okay, next time we're going to get into quadratic formulas. Cool stuff.